What is up, multivariate gang? Today we're going to be talking about orthogonal decomposition. All right, orthogonal decompositions. Orthogonal decompositions is the process of breaking a vector down into its components along two orthogonal unit vectors. Orthogonal, of course, meaning that they're perpendicular to each other. So we've got our vector v. We're going to pretend that these are one long because I'm bad at drawing. We've got two unit vectors perpendicular to each other. E1, give those little hats. E1 hat and E2 hat. All right. So we're looking for the length of this line and the length of this line. The lengths of the lines parallel to these two unit vectors. So if we know our little angle theta, we know that this edge over here is the norm of v times the sine of theta. And this little piece is the norm of v times the cosine of theta. And you can verify me on that if you don't believe me. That's just some trig stuff you guys probably should have done in physics. All right. Now, that's if they give us the angle. They're not always going to give you guys the angle, so you need to be able to find it without the angle, like if they just give you the components of the vectors. So there's another way to do this, using the dot product. So we know that v dot e1. Actually, back up. All right. No, cosine theta. Nope, I was right the first time. Sorry, guys. We know that v dot e1 hat equals the norm of v e1 cosine theta. Well, the norm of e1 is just 1, so I know v dot e1 hat equals norm of v cosine theta, which means that this piece right here is equal to v dot e1 hat. Easy enough. Now, if you can imagine, if we had this angle over here, call it phi or psi, that this piece right here would just be norm of v cosine of phi or psi, and we could do all the same math here, except E2 instead of E1 and phi instead of theta, and we get that component right here is equal to v dot E2 hat. Easy enough. So this length right here and this length right here, those are called the scalar components of vector v along E1 and E2. Now, when we multiply those lengths, those magnitudes, by the actual unit vectors and give them direction, well, we get our vectors, v's vector components along E1 and E2. And if we add those two vector components together, we get vector v. So this vector right here is v dot I1 hat times E1 hat, like a scalar multiplication. And this guy right here is v dot E2 hat times E2. Scalar, since it's dot product, scalar multiplication. All right. So that means that v that plus equals v dot E1 hat times E1 hat times the vector E1 hat plus v dot E2 hat times the vector E2 hat. Simple enough. Let's do some example problems. Change the color. All right. Find the scalar and vector components of v along E1 and E2 if v equals 512, E1 equals 1 over the square root of 2, 1 over the square root of 2, and E2 equals negative 1 over the square root of 2, 1 over the square root of 2. Okay, so scalar along V1, or E1, I should say, E1 hat. And I didn't put the hats in because I don't know how to do that on Google Slides. Equals v dot e1, which is 5 times 1 over the square root of 2. Let's go and rewrite these. 1 over square root of 2, square root of 2, negative 1 over the square root of 2, just so we know, so everybody knows what we're talking about. Cool. Plus 12 times 1 over the square root of 2, which equals 5 over the square root of 2, plus 12 over the square root of 2, which equals 17 over the square root of 2. Our vector component along E1 hat is equal to our scalar component times E1 hat. So 1 over the square root of 2. Whoops, forgot to put my square root of 2. 1 over square root of 2, 1 over square root of 2. That's just scalar multiplication. That gives us 17 halves, 17 halves. Easy peasy. All right. So our scalar along E2 hat, it's going to be v dot E2, which is 5 times negative 1 over the square root of 2. Just multiply the x components, plus 12 times, multiply the y components, 1 over the square root of 2, which equals negative 5 over the square root of 2, plus 12 over the square root of 2, which gives us 7 over the square root of 2. All right. And finally, our vector component along E2 hat, we get our scalar component times our vector E2 hat, which is negative 1 over the square root of 2 times 1 over the square root of 2. And we get scalar multiplication, negative 7 halves and 7 halves. All right. Now, just to double check our work, if we add this and this together, we should get our vector v. So 17 halves minus 7 halves, 17 halves plus 7 halves. That gives us 10 halves, 24 halves, which equals 512, which is our original answer, or our original vector. Boom. Easy enough. Onwards. Sometimes they do give you the actual thing, and then it's easy. Ooh. And ignore that. Ignore the vector component part. I meant to take that out. I just forgot to when I was writing the question. Okay, find the scalar components of v along E1 and E2 if v equals 512 and the angle between v and E1 is 30 degrees and the angle between v and E2 is 60 degrees. Easy enough, not that hard. So we know that our scalar component along E1 is just the norm of v, which square root of 25 plus 144 equals square root of 169, which is 13, Pythagorean triple. Norm of v times the cosine of 60, which is 15 times the square root of 3 over 2, which is 15 square roots of 3 all over 2. Then, do our scalar component along E2, which equals, I don't know why I added that. That part's redundant. we can ignore that. We know that it's norm of v times the sine of 60 degrees. Wait, what? What did I do here? Oh, I did something wrong. Sorry, guys. That's 1/2. I forgot my stuff. That's 15 halves. Here we go. That's 15 times square root of 3. 15 squared root of 3. All over 2. Cool. I don't know how much you guys actually have to do orthogonal decompositions in the homework or just in life, but there it is. And we will talk about an application of orthogonal projections, or the orthogonal decompositions called orthogonal projections in the next section, which is the last section, which is the last video for this section. You guys will be 3 sections.